A very good morning to all. It's my pleasure and privilege to welcome our former Union Minister for Human Resources and Development, Government of Karnataka, Dr. M. Pallam Raju, who is an Government of India, who is an electronics and communication engineer with an MBA from Fox School of Business and Management at Temple University, USA. Complex business environment before starting his political career. A warm welcome to you, sir. A hearty and warm welcome to our distinguished speaker, Dr. J. N. Reddy, Professor of Mechanical Engineering, Texas A&M University, USA. A warm welcome to you, sir. A very warm welcome to all the dignitaries of the dais, head of the departments, and faculty colleagues present here for today's program. I now request our respected principal, Dr. N.B.R. Naidu, to lead our distinguished speaker onto the dais and introduce our distinguished speaker to the audience.
Oh, sit there. Very good morning to Canada here. On behalf of Rama Institute of Technology, Local Education Foundation, and on my behalf, I welcome the Dr. M. Pallam Raju, former Minister, Human Resource Development, Government of India, Dr. J. N. Reddy, Professor, Texas A&M University, USA, our Chief Executive, Chief Financier, Dr. Ravidan sir, is the Quality Assurance Head across the GEF, all other representatives from the various GEF institutions, the HODs, faculty, staff, and my dear students also, who join offline as well as online for the distinguished for the lecture on on competition mechanics by J. N. Reddy today. I just briefly give 2 minutes. Very brief because of the running of the time. I'm not going to give in detail about Professor J. N. Reddy sir. He is a distinguished professor, Regents Professor, and an annual holder of the Oscar S.Y. Endowed Chair in Mechanical Engineering at Texas A&M University, College Station, Texas, USA. He is the authoritative figure in the area of mechanics and one of the researchers responsible for the development of finite element methods. He has made significant contributions in the areas of finite element method, plate theory, solid mechanics, mechanics of composites, functionally graded materials, fracture mechanics, plasticity, biomechanics, classical and non-Newtonian fluid mechanics, and applied functional analysis. He has completed his BE in mechanical engineering from the Usmania University, Hyderabad, in Andhra Pradesh in the year 1968. He completed his MS in mechanical engineering, Oklahoma State University, Stillwater, Oklahoma, in the year 1970. Later, he did his PhD in mechanics from the University of Alabama in Huntsville, Alabama, in the 1973. Followed by postdoctoral fellowship at Texas Institute from the competition mechanics, University of Texas at Austin in the 1973 to 74. Reddy has over 620 journal papers. He has authored 20 books. He has advised around 36 postdoctoral fellows, 65 PhD students, and 46 MS students over 40 years. He has been listed as an ISA highly cited author in engineering by the ISA Web of Knowledge Thomson Scientific Company. Reddy is one of the original top of 100 ISA highly cited researchers in engineering around the world. With the index of over 66 as per the Web of Science, the number of citations is over 54,000. With the index of 94 and I-10 index of 438 as per the Google Scholar. Dr. Reddy is the recipient of many awards and honors. To name a few: the Timor Simcoe Medal, American Surgical Mechanic Engineers, 2019, ASME Medal, American Surgical Mechanic Engineers, 2016, and many more awards. He is also a Satish Dhawan Visiting Professor, Department of Aerospace Engineering, Indian Staff, Science, Bangalore 2013, Distinguished Teaching Fellowship, the Royal Academy of Engineering, London, UK 2013, and many more. The list is endless. We are honored to have a scientific figure of his stature among us today to share his expertise in the area of computational mechanics. I welcome you, sir. Now I request Dr. J. Reddy, sir, to take over the session. Thank you.
Thank you. Very good morning to you. So, whenever I get introduced, I really feel a little bit impatient because I don't want to hear about myself. I want to hear about you, right? And these days, there is not that much privacy. In fact, there is so much published on YouTube or Google, and I sometimes look at it and say, oh, did I do this or did I go there? Because they have everything there. And I might have forgotten, but they have everything. So I'm sorry to say, whatever you said about me is almost 10 years old. Okay? So you go look at the Google citation, all of those are different now. Okay? So, but thank you for introducing me with all those things. But I'm just trying to be here to help and maybe communicate some things that you maybe find it interesting. This is a research talk compared to the other talk. So it would be technical, but no equations. Okay, so Dr. Palandraju doesn't have to read any equation. Not that he cannot, he can. Okay, all right. Is it going on the end? Doesn't work. That had nothing to do with this. Very it's working. Thank you. That's all I need. Okay, so I will always start with some general remarks. Then I'll talk about the role of computational mechanics. So there are two words there, computations and mechanics. Mechanics is a very broad word which deals with the fundamental understanding of any phenomena under the sun. Anything, okay? Fundamental means very basic understanding of that phenomena. So these two together, you need to go from understanding the phenomena to predict it. And we want to use mechanics to predict whatever things that we study, or we make them and we want to understand how they behave, right? So I will tell you, then I'm going to, I may reduce this because of time. But those are the three areas that I'm working currently. One of them is architected structures and materials. which I was talking to some of you in the audience. I think it's a very rich area for developing and exploring and damage and fracture. And then I will also present some research topics that may be of interest. Okay, so there is really a 4 or 5 topics that you may find interesting to pursue. And you may be already working, okay? So let me do that. Then I will close with some remarks. So let me start with the view of mechanics and modeling. So I always say it's my view, you may not agree with it. So everything engineers do is model. So the word model means you're trying to represent the real world situation as something that you can actually write in analytical form. That means with the help of the laws of physics, you will create equations that govern the pertinent information, okay, or relationship. In nature, everything is cause and effect, and I call this duality. A force causes displacement. You understand that one, right? So that is dual variable. So that is really everything that we do is modeling. And the word, it's not necessarily think that it is a model does not mean necessarily that finite element model or something. So model is a representation of the reality as a engineering problem. Okay, so that you can solve it. And so modeling requires mathematical and computational tools. So that means how do you represent something in analytical way? Right? So biological, geological, mechanical, all of these phenomena has to be represented as equations so that we can use computer to solve them, to understand the phenomena. And so that understanding we take to the level of design and manufacturing. So there is no complete mathematical model. See, this is something many, whether you are a professor or a student, you tend to think all those things which are in the textbooks are exact. That's far from the truth. Those are models. We are happy that they're working, but we should not close it. It's an open box. It is still has option or opportunity to extend. Okay, so in fact, there is no such thing as complete mathematical model. As we learn more, we add things to it. Okay, so there's so much to understand. So we never should think of I closed my mathematical model and I don't have to improve it anymore. That's not the case. We only try to improve on what we already know. That is research. Okay, so whatever is already done by our forefathers or our colleagues. Okay, you remember Newton said he's looking over the shoulders of the giants, able to see further, or farther, both, right? So only because those people have done, and I'm beneficiary of those ideas, and then want to take to the next level. So that is really all we do is to improve what we already know. And the other thing is there are only 2 things that matter in engineering. And this probably is true even in the other professions. One is the functionality. So knowing the probability of failure. Functionality means is everything that we make as a functionality or multiple functions. But knowing when it fails is important. That is where actually design comes from. Okay. And then secondly, we want to make sure the cost of the product is small. It's a relative word. And but these two don't go together, and you need to make judgment, or you meaning whoever is ultimately selecting the design for manufacturing on the basis of which one is more important. Which one means is the functionality should be put to greater value than the cost. That means I'm willing to pay, but I want more reliability from the component. And that's the case with biomedical equipment, prosthetics, because human life is at stake, right? So we want to spend more money to make sure that it functions. Whereas some other things that are not involving human lives, we can make it cheaper because we can repair it in case if they fail. So this judgment comes from the designer depending upon the application of that product. Okay, so the role of engineering science in the society is very important. I mean, we all have to be driven by how we can improve the existing products or come up with new ideas to implement for the benefit of mankind in the form of health, okay, transportation, communication, and of course, ultimately also our safety depends upon the borders, right? So defense structures as well. So, and of course, that is a very broad topic. There are so many aspects to when it comes to research for defense. So in most of the cases, engineering is trying to solve those technological problems. So that is why engineering is a problem-solving discipline. And so the subjects that you take, especially those students who are in the audience, I like to tell you that the subjects you take are very important. Never underestimate the value of what you learn in the college before you go take a job, because it provides you the concept to formulate when you set up the problem, right? And then nobody is going to give you nice cantilever beam with uniformly distributed load, find the deflection at the end of the beam. No, they will only show here is the bridge, or this is what I want to do, bridge from this band to that band, a particular bridge. You tell me what kind of bridge would be good, how long it will last, what is the cost of it, right? So formulating is the most challenging thing. You will not have the pure banana like you have in the class. You have to come up with those ideas. But the ideas come because you have a subject, rational thinking, mathematical background. Okay? So formulate, analyze, design, and make a decision. Making a decision, we don't teach enough. But decision making is a very important part of engineering. If you cannot make a decision what product or how you want to select the design, then it's not good. You have to make that decision. Okay? And then we have to, this I want to, especially since this is the academic base, I say knowing fundamentals. The subject is empowers you. And it increases your confidence in yourself, and I can do attitude to develop. See, otherwise you will be talking kind of, ambiguously. You don't communicate with confidence. So don't get into the situation of where you don't really feel comfortable of talking about a technical subject. Because if you don't have background, be forthright, honest, and say, I don't know enough about that. Because not everybody is, expert in everything. That includes me, right? So it is, but you have to think of whatever subject area you're working, you must know that subject area fairly well, both depth and breadth. And so that you can communicate with confidence. Okay, so now I want to say how computational mechanics works. As I already mentioned, we need mathematical model of the physics, whatever you are modeling. Mathematical model means set of equations. It can be differential equations, algebraic equations, and the combination thereof. But these are so complicated, mostly because of the boundary of the system. So it's not nice rectangle or circle. And also the couplings, lot of phenomena going inside. The equations are highly nonlinear and coupled. So there is no way you solve them using your knowledge from mathematics. See, those are only to give you kind of your feedback to understand that a second order equation requires two boundary conditions. That kind of general knowledge. But you cannot solve real world equations with those techniques. So you have these numerical methods. And finite elements is one such method. So what I'm going to just call it computational mechanics. So the modeling, realistic modeling of physics is empowered by numerical techniques. See what happened for ages, because of complexity of solving those equations, they simplified by omitting terms. That is amounting to omitting the physics, part of the physics. So now we are empowered because of computers, and numerical techniques. So we can challenge ourselves how much information I can include. But only we can include that what we know. New information means that has to be researched. Okay, whatever you include is that's what you think is happening, that numerical methods allow you to explore. See, if you want to do experiments, you don't know how to even build equipment. Whereas any time consuming and also costly. So whereas numerical technique, you can sit in your office, work on a desktop, and you can try all kinds of geometric configurations, including destroy all kinds of geometric configurations, including additional terms or additional phenomena, and see, oh, what if I change something? Like think of an aircraft wing. So if I modify a little bit at the fin or tip of it, what kind of aerodynamics is going to take place? Is it going to create more turbulence or much more smooth? So these are all done as if you are just playing a game, right? So this is the advantage of computational methods. So they allow you to explore alternative configurations, choice of materials, and host of other things. So it provides you the design alternatives. And computational mechanics is the key to many developments. It has been going for several decades, at least 5 decades now, if not more. It has become the tool, day tool in industry. Many of you may not know, but again, I will bring finite elements into focus. That is how most of the designs are being analyzed and made decisions are made before they actually take it to the manufacturing group. So it is really very, very important, and it is also used as a tool to explore new physics. So it is being used by researchers, developers, and designers. So it is a very powerful, and it is not just in mechanical or civil, it goes cuts across the disciplines, biology, chemistry, even economics. All we need is a model, economic model with coefficients that depend upon ethnicity, religion, climate, all kinds of things. Developing that model, people won Nobel Prize, right? How do you solve that? In these computational schemes. So it is really a very, very broad computational tool. Okay, so this gets a little technical, but I want to be finite elements, finite volume, finite difference, all these methods divide fall into parts. And all of the parts are really ultimately means points. More points means more accuracy, because you are including every more points of the domain. Okay, so the details of these methods differ. The first one is finite element, second one is finite, meshless method, third one is finite volume. This is more popular in fluid dynamics. But all of them share one thing. All of them at the end of the day have points. At these points, we want to know what is the cause and effect relation. Cause and effect relation. How the forces at these nodes or points are related to displacement at those points. How the temperatures at these points are related to the heat input to the system. And you want to solve that, right? You will give temperature and find the heat or vice versa. At every point, by the way, not just one point. So we have that. So it is ultimately nothing but coming up with the algebraic relations between the duality gates at all these nodal points. More nodal points means more accuracy. So the exact solution would be at infinite number of points. But we don't have that facility. We cannot have exact solution. So the next best thing we can do is to find it, select few points. This few could be trillions. Okay, not just 10 or 15. And but that imposes restriction on the resources we have. Okay. So if you think of a aircraft, so it may have millions of these points because every point fuselage to wing, aileron, and also the dome, control dome, all of these have to be modeled. And every part of it has a different aspect, physical aspect. Okay, so it is a couple of phenomena: aerodynamics, which is the fluid mechanics, then it is the structural aspect, and heating, because it is the friction causes the aircraft to begin to heat, and once it reaches 29,000 feet or 30,000, then it's very cold, right? Temperature changes. All of these induce stresses in the body of this aircraft, and they have detrimental effect. So when we design under the action of all these external stimuli, it's still intact. That is what it is. I mean, sometimes you marvel about your own work. Really, we are able to do it. I mean, think about automobile. You are the one who get tired driving it, as long as you feel the fuel. See, compared to 30, 40 years ago, they really don't break that easy. So much reliability in what we make. So anyway, that's a little more technical detail. So I will give you one of the areas that I work is there are commercial programs called AMC, Abacus, and so on. These are used in real world company simulations, whether they are designing aircraft or a automobile or a heat exchanger, any of these. Finite elements is there in the background, it is crunching numbers. So one of the areas I work is shells. And shell is a general thin object. Thin means thickness is small compared to the radius of the end and length of the shell. And these shells could be, your eardrum is a shell. So it could be shell could be mechanical or biological. So one of the things that happened in commercial course is they made a lot of restrictions. So my interest is to remove those restrictions. Many of the restrictions is only because the mathematical model they have is not inclusive. For example, thickness changes. So just think of this body, even if you're not a mechanical engineer, think of balloon. Okay, and balloon, you blow air into it. What happens? It expands. When is the surface coming? I'm just asking, when is it coming? It was only small piece, and you blew it, it became big. So the material is flowing into the surface, right? And if you keep blowing, then it bursts because it became so thin, it's not able to take the stress anymore. Blows, right? So the thickness of the balloon is changing as you blow. And same thing happens. If you really put internal pressure, it is going to enlarge. But the material is flowing from the thickness. And that thickness stretch is not included in the commercial course. So I wanted to explore that, and that's what we have done. So the problem with this is now I cannot play videos because I'm not using my computer. So these are the limitations. So I cannot include any of these. So I was going to show how this is going to expand and show how thickness changes. So I cannot do it. But it is shown. So one of the things that I'm showing here is I compared the results with ANSYS, Abacus, and each of these programs, commercial programs, have different types of elements. The shell elements that they have, see, these two are shell elements which are showing this response subjected to the internal pressure, which is listed as a characteristic load, and the stress generated inside is that point. So you can see as you increase the stress, load, the stress goes in this fashion. and both programs predict that very nicely. But remember, these are sharp. If you go to three-dimensional elasticity, means you have really refined the model now. Because then 3D has this ability to show the stretching also. Then that result is quite different. See, it's here. And ANSYS predicts this, and Abacus is predicting. To a large extent they agree, but then small deviation. So whereas the element that we develop is coinciding with the most accurate theoretical model you can have. So that means this shell element of the commercial code is not predicting the correct result compared to the true result, whereas ours is able to do that. Because we included the ability to capture the stretching of the thickness. Okay? So this is, how we make the advancements. And then we might say, oh, why don't we use the 3D elements from the commercial code if it is really giving the same result? Well, we care about computational cost. So the elements that we develop only take very small number of degrees of freedom compared to this. You see that order of magnitude and the computational effort. So that means we can use the shell element, get same 3D finite element solution by the commercial course. So that is the actual model of the story. Now I come to this architecture, materials and structures. So these can be in any, whether it's an aircraft, and of course when you walk into the airplane, you don't realize that there is a lot of deck inside, and the deck can look like this. So there is a corrugation or all kinds of structures. So you only walk on the top, and of course that is carpeted, you don't even see the structure. But underneath it has all these things to take the strength and stiffness to take the load, right? And yet in flying, it has to keep the aircraft intact. So how do we design those? And this is becoming very common now. We are manufacturing with the help of additive manufacturing. A lot of custom made parts and very miniature to very large structures, like ship structures. So all of them require designing the material, the core. The top, what you call the top and bottom is one thing, but the core structure is very solid, which is designed such a way it has the least amount of material given, but the most strength and stiffness you get. But the problem with that structure is how do I analyze this complicated thing? It will take a lot of degrees of freedom. So we have come up with a way to represent this using so-called non-local mechanics. So this is not a place where I want to go into deep into that. But I tell you that this non-local mechanics is about what mechanics you're learning in your class. So that's what I meant by saying mathematical model you study is not complete. So we make it relatively more complete, and yet still not complete. Okay, so it's key. We always have room to improve. Anything and everything. Okay, just like our knowledge is never complete. We learn, keep learning every day. Okay, degree getting is one thing, but that's only an eligibility type thing. You never really know everything around you. So, and there are many kind of structures. Now we want even foldable. Okay, fold it and for transportation, very simple, and when you go to be placed, when they have to be placed, you erect them. So all of these mechanisms, foldability, all that. So how do you study? And it has to be only through computational mechanics, numerical simulations. So, but you also have to pay attention to the cost of simulating. In fact, even present day computers may not have the memory to solve every little bit of it. So we have to find a in-between. That means you don't represent every ligament of the structure, but only some main features that you are looking for. Okay, reduce the computational cost. And that's what we have done. And so when and I won't go into it. This is some few mathematical meaning for showing. I have to show you. So these simplified equations may still complicated, but the very complex structures. So you can see this web code with the top and bottom, and there are webs which are taking the load. And I highlighted here one such. So we can solve this as a typical, what you call unit cell, and then correlate the response of this for the entire structure through a mathematical model. And this is where we bring non-locality. That means a point not only translates, but also can have rotations. This is what non-local mechanism is. We have not accounted for that in the past, but now we can do it, and we represent the energy equivalently, the true energy of the structure with all the details taken in an academic setting is equal to the energy of this alternative mathematical model. So the energy cannot be different. That is the basis on which we connect the highly refined model to relatively less refined model, and be able to solve a lot of different problems. So I'll show you just one example. Okay, so this, if you look at a load here, a line load, and so it is going to reflect. What I'm plotting here is the displacement along the length. So according to the three-dimensional finite elements, which is the most accurate, okay, relatively speaking, that is the response. We see the dotted line, and with our micropolar non-local theory, we get almost there. Very, very small difference. Whereas the existing or the classical ones, they predict very lot of error. Okay, so again, this is improvement. So by the way, I have to be very candid here. The difference between what is called exact and what is this approximate, that error may be tolerated in some designs. Then you don't have to go to this number. So I'm not trying to sell that for everything. You don't kill any ant with a sledge formula, right? Okay, you can just use your thumb. But where it is needed. So that is what we are doing as researchers. Develop the tools for the benefit of who needs them. Okay? All right. So this is the third topic, which is really a track shifting. This is the real experimental result. This is our simulated result. And again, because I don't have the ability to show, but it will show, this is all this red is ultimately showing how close it came. See, if it is exactly representing experiment, then you will doubt my work because you did something to match it. Okay? The reason a computational tool cannot exactly represent experiment is the material property. Because material properties are to be input to the computational code. Whereas in the experiment, it doesn't need because it's built into it, right? So any error that you have in the characterization of the material can lead to difference in the prediction by computational tool and experimental result. But we are able to predict very close. And so this is another thing, the concrete slab, if you push it here and you kind of intuitively think, the traction may start here and propagate. And that's what happens. And there are many methods. Again, I cannot show the propagation because of the video issue here. Okay, all right, let me see. Okay, so this is something why I put this here is engineering is always an approximation. It never gets so-called exact, and it doesn't make sense even to talk about exact because there is no such thing. Okay, it all depends on so many variables, but getting close enough. So this fellow, British economist John Maynard Keynes, said it is better to be roughly right than precisely wrong. Okay. So, because you can create mathematical models, they will predict something, but that is not reality. So, you want to create mathematical models and computational schemes that are at least approximately telling. And by the way, designs are based on a bandwidth, not on a precise number. Because the vehicle or anything, it doesn't work in that range only, works in a broad range. So you want your design to accommodate that. So we don't need to find things for a specific load. We want a range of loads for which it should be safe. Okay, so now I come to the actual challenges. I would say few topics. One of them is coupled multi-physics problems. This is a very important area where it connects mechanical engineering to biological engineering, for example. Multi-physics or structural mechanics to heat transfer or fluid dynamics. Because in the real world, they don't act one. All three may be present. Okay. So coupling problems is one major area. Second, multifunctional materials modeling. Multifunctional means now we are making designing materials with multifunctionalities. That means the structure should take the loads, but at the same time it should have less conductivity. Okay, or it should have sensing mechanism, sensing and actuation. So all those functionalities you can build into your structure, including that architected structures I was talking about. And of course, third is computational biology and chemistry. So those, when I say word computational, biology and chemistry is a lot of phenomena, observable thing, and then they plot this and that, but there are no mathematical models because we do not have the laws of biology. So we don't sit back and say, I don't have laws, so I don't do it. Just like engineering didn't have laws of physics. Newton's laws didn't come until 12th century. But a lot of people built all those temples in this country and all those alloys, copper alloys, all that. How did they do it? They did it understood by doing it. When they failed, they found another way to try it again, right? So that's what's happening. In biology and chemistry, we study experimentally and then find way to characterize a mathematical model. And then bring computational tools to study. So there are a lot of things that in real world we do. So of course this is sport vehicle, and you can there are so many components in a given thing, and if you are so focused about the terrain is going to soil structure interaction, right? And soil is not going to be one. When you dry, the soil is not same homogeneous everywhere, right? It's different. So how do you bring that soil interaction with the variability in the soil properties? Okay, so and then the material of the tile itself has an influence on it. So the traction and also maneuverability, all of those we have to study. Interaction, soil and structure interaction, or crash test. And in automobile, we have so many components, right? So everything that you do has a multiple objectives or phenomena that they are representing. Okay, so this is kind of showing how nanocomposites come into picture. Different parts of the, compared to 30, 40 years ago, we didn't use composites that much. But now, because composites was used mostly in defensive applications, missiles or aircrafts, fighter aircraft. But now we are using them in civilian. So Boeing 787 now has 51% composites. Okay, same thing with the Airbus. So what composites do? They bring strength and stiffness and lightweight. Lighter weight means more passenger capacity or more fuel capacity so that you can go longer distances. Now we travel without refueling as many as 16 hours in one go. That is the places I have traveled, I have been in the aircraft 16 hours. One from Newark to Bombay is 14 hours, some 13 minutes or 23 minutes. One from San Francisco to Bangalore is more like 16 hours. So probably it can go even further, but that's right now. Because you always have to build this safety thing. in case there are headwinds and a lot of consumption of fuel, right? Okay. Anyway, so I'm just flashing three things. Infrastructure, nanocomposites infrastructure. Not only the platforms or barriers between the highway and the residential community to arrest the sound, right? Acoustics. Or you think of concrete slabs. So this is what we call vent test to study. So this concrete will have self-healing capability. So healing means it may develop fractures. So we make it so that it will fill up those cracks, self-heal in that sense. So that means you are bringing some chemical agents embedded into the concrete. So there are many things, and then you can go into biological side, human. So including understanding how heart functions, okay, and you growing the cells for if you have a burn victim, you don't wait for months and years to heal. You prepare the skin growth in a lab, you just graft it. And it only takes short time. Of course, if you're younger, it will take a shorter than for people like me, right? So we are there now. We are able to do these types of things. And breast cancer. And so, see, doctors are really more trying to help you diagnose and prescribe. This prescription largely comes from the recommendation of the pharmacist, right? But it is always broad spectrum specification. Drugs or medications are not designed just for the person. We are getting there, but it takes some time. Okay? So patient-specific treatments are there, but prescription of the patient-specific medications is not quite there. Same generic medication, everybody has the same type of disease, they will prescribe the same medication. Okay? So those are the kinds of things. So there is a lot to be done. These are generic things to say, but behind the scenes, there is research to be done, identify the mechanisms, and then represent in analytical form to actually solve for the unknowns. What is that unknown? Location of the cancer, or the rate at which the cells are moving from surrounding to that point, right? So all of those are embedded in the mathematical model. Okay, so I have 5 topics. Materials design. This is the architected material. That means we are designing materials for the functionalities we want. So there is a lot to be done. And most important thing is to understand the structure-property relationship. The structure you create and the properties they exhibit. Properties means modulus of elasticity or strength and fatigue life, things of that nature. Okay. Then second is simulating manufacturing processes. See, we learn to manufacture, like if you create a composite and machine it, it may be actually getting damaged during the machine. So understanding that and creating tools that are different, cutting or reshaping the composite or whatever that material. So change from improving by doing to improve by reasoning. That is what we have to do. See, it cannot be just keep doing and checking, let me see if it works. Then you are wasting a lot of material and time. So you have to bring the element of thinking, reasoning. So I'm not reading these, but just saying, now with the 3D printing revolution around, we are into 2 important shifts, making and building. Okay? And most of these are custom parts. 3D printing is, like if it is a, for example, an aircraft, and it flew from one country to the other, and when just before arriving, it developed some cracks somewhere, and fortunately, it landed safely. But you need to fix it, right? So that part, you don't go and order from somewhere. You should be able to produce on-site, custom part, with 3D printing or whatever it is. Okay? So repair technologies have to do that. And the smart systems with integrated functionality and safety. And that means you make things, but they also should tell you in case if there is something wrong happening. Like a pilot should know if the track develops in a wing, on his dashboard or her dashboard, it should show something going wrong in that car. So that they take immediate precaution to land in the nearest airport, right? So we have to put those kinds of functionalities into the design. And so device based to learn retail properties. So this machine learning is a big thing, but it is a tool. And machine learning is a computational tool. There is not a physics there, right? So we are trying to develop ways to assess the damage or trends that are occurring in that structure. And lastly, computational mechanics for multiple. See, the computations is everywhere. In fact, all the advances that are being made in technology, a tool, computational tool is behind the scenes. Okay, because it is providing the designer with the numbers to make a decision. So it is very important that we develop or refine the existing computational tools to be better. All right, so I will just close by saying that whatever we do, they should be based on fundamental understanding of things. They cannot be just ad hoc theories. Okay, so it has to be sound. The word mechanics is everything. Okay, it's in heat transfer, fluid dynamics, structural mechanics, biological aspect, geological aspect, fundamental understanding why it is happening, why tsunami coming, why certain place tectonic physics, earthquakes come. So we need to understand, develop the mathematical models of it in studies with a goal to predict them in advance. Okay? I mean, when it comes to tsunami and earthquakes. So, in second, we must develop computational tools and refine them. And the equal important is we have to do few experiments because mathematical tools may be predicting wrong things. So there has to be something that validates it. And the experiments are the one. But we cannot afford to develop experiments for every little change we want to make. It's costly, time consuming. So once you validate, then you put all your trust, faith in the computational tool. That's what is happening. Okay? And the challenge for the mechanics, again, the broad word, is to regain its place in the decision making. See, this is not happening enough. Because most of the units do things, but they are not at the decision making, because it's the administrative people make the decisions. So we have to give or put ourselves in a position to tell them. See, a lot of failures that have happened, including one of those O-ring space vehicle, because the management thought, oh, that's not important. Okay? Even though there was engineers who told that there is a problem. So sometimes either to meet a deadline or to cut the cost, they think it's not going to happen. And this is where we have to be part of the decision-making table. We meaning engineers. Okay? All right. So, and I think I will just stop here. I will just say research advice to especially young people. You must keep the long-term research objectives in mind. You cannot be going all over the place. You have to focus. Time and depth is two things. Without having enough time invested in the topic area, you don't really make a contribution. You just only scratching the surface. So you must. And specific area that is very important, and you go in the area that is not too many people working, then you won't be known because they're already ahead of you, right? It's not easy to catch up and make it. It's possible, but it is more difficult. Conduct research that may be relevant to industry and ultimately to society. So that's the one. Then, a sense of feeling satisfaction. That's something I did, even little thing, that made an impact or contribution to society. And organize your time around teaching, academic institution, service to the, and then research to service to duty. These two things may be scheduled event because a meeting, a conference, or the teaching a subject or class, they are scheduled. So research is not, so you have to really organize discipline in the way that you don't postpone. All right, so I think these It is in fact not the numbers. I say this because where I am, I can do that. But many of you are playing the game according to the rules set by the people above you. So, only two options you have. Quit the game. That means leave. But if you are in the job, playing the game, you have to follow the rules. So that's the way it is, right? If you are playing cricket, you have to play according to the rules of the cricket. So now I will not play according to that. I have to do. Until you reach to the place where you can change the rule. So, since many of us or you are not there, you must. So, what I'm trying to say is, you should really keep impact in mind. But I said not numbers, that is true, but I really believe in that. But numbers also are important because people count them. So, I'm being realistic. So, you have to learn to crawl before you run or walk. And then you learn to walk before you run. Meaning that you learn to publish, even if they are not very impact factor journals. But then you start publishing enough, then you say, oh, I want to publish in the best journal of my field. That's how I want you to think. Okay? Don't say, oh, I'm going to publish my very first paper in the best journal. But that may take several years. In the intervening years, you are showing zero publication. And that is a red flag for your administrators, right? The leader or department head says, you didn't do anything. You can give a good excuse, say, I'm working, I'm getting there, I'll be there. No, nobody will listen. So you play the game according to the rules. So I already said this. When you create any kind of new invention, make sure that it is going along the right direction. Okay, right direction in terms of physical prediction, whatever that your field is. So James Bryant Conant said, science advances not by accumulation of new facts, but by the continual development of new concepts, ideas. Okay, so this is important. Okay, I will just close by saying that let me see. The pressure to publish is always there for academic. So don't get blinded by this. Some of these slides I took from yesterday's talk because I wanted some of you to revisit. So public, it has a negative impact because you are in a hurry to publish and really doesn't have much to give. So you have to judge really this time to publish, or should I explore a little bit more, make it a little more complete. So that is in your hands. So be careful about that. At the same time, don't only look at citations, impact factors, because they have been manipulated by the reviewers, by the journal people, and fellow researchers, because they are focused about only increasing the number, even if they don't have impact. Okay? So it's not necessarily the best measure, but it is a measure. Again, as I said before, since that is used, you have to get citations. Okay? But don't just put all your heart into getting the artificial citations. It should be really come from people who think your work is worth citing. Okay, so do not worry about citations or H-index. So just try to do the best work you can. And then tenure, I don't know the system here, but I'm sure we have a tenure system. So you will get it if you do the right thing, focus on your teaching and really with passion to facilitate learning of the students, because teaching is one of the criteria for earning tenure. And then do research. So those two will, and service of course is something we all have to do in our own way, smaller to higher, depending upon if you're a young assistant professor, you do little few things. But as you get senior, you start giving more time because you took the more time from me when you were young. So it is time to be back to this department or college or whatever. So don't always think of what is in for me. Okay, so All right, I'll just say, this I said before, I want to say one more time, or works have to be built on a very fundamental way, the basic engineering principles. It cannot be ad hoc thing. And we must develop computational tools that are robust. Robust means they are very fast, at the same time efficient, without having ports, meaning there should be no tuning things. Because then you are trying to predict what you want. Okay? So the model should predict what is happening in reality. And physically meaningful experiments. So this slide is a repetition because I'm kind of concluding what should stay with you when I finish this. The challenge is to get back to the decision-making table. Engineers should be part of that. Okay? They should be respected for what they do. So I thank you, all of you, for being here, listening to me. And I may not know everybody who actually made my visit and lecture possible, but Dr. Naidu is, of course, one of them. Sorry, let me. So the chancellor is not here, but right, he's not here. That's right. Okay, so but he was one of them, and Dr. Sai Baba is not here, but he's also pro vice chancellor is here. So. And you can see many of you who made it possible for me to give this lecture. And I enjoyed it speaking my mind, what I think is right thing for you to know. So if you have any questions, I'll be happy to answer. Yeah, I have time to whatever to tell. Well, whenever the chef says, "Oh, we have to go," we'll go. Yeah, eating is not that important, but I want to, see, especially young people. He may have quite general questions. It doesn't have to be, "Oh, how is that problem solved?" I can explain, but it will take a lot of time, and you also have to have the background to understand, right? But you can ask general questions. Anything that comes to your mind about the career, or where you want to be, what you want to do.
Any questions from the audience?
Or comments? Doesn't have to be always questions. Looks like you're tired. I didn't understood everything so well. Okay, there is a question.
Sir, there's a question.
Somebody has to break the ice.
Yes, certainly. So I'm Prakash from Going India, and thanks for a nice talk. A lot of interesting ideas, especially for the benefit of the student. I have one question. You briefly mentioned about the machine learning. So I would like to know your thoughts on, as a computational mechanics person, do you see opportunity in it, and do you also see threats in it?
Yeah. So this is a good question. Machine learning is a invention by mathematicians and computer science people. So there are two kinds of machine learning algorithms. One is aided or supervised, other is unsupervised. So, but either one, I won't go into the detail of the difference. Obviously, not supervised means you have something to tell it where to go. Other one is let it do whatever it needs to do. But all of them depend on the data. Data means you conduct experiments on something, okay? Either you're studying heat transfer or structural. The data has to be there, right? Force deflection relationship. And that data goes into this algorithm to find trends. Trends means the stress increases with the geometry, somewhere changing, or load, of course, that is obvious. So, but if the data is not coming from the good experiments, then you have a possibility of wrong prediction. Okay, the data has to satisfy the principles of that field. That means there has to be a certification of the data. That's how I think. Unfortunately, it is driven by computer science and mathematics people who Only thing, this is called, by the way, new field called data science. And really, the word science is not much there. The science requires you to follow the rules of that particular physics, meaning satisfy the physical laws, conservation of mass, balance of energy, balance of linear momentum, and so on. If that data doesn't satisfy that, then you should not use that data. So that's, but there is room for you to improve. Okay, I don't want to take a pessimistic view on the one, because it is as a potential to help. And so the most important thing about that is if you have data from experiments, valid data, you don't have to do too many more experiments. So it will tell you that these are the trends. You can use these trends to design whatever you need to design, whether it's an apparatus or a component of a structure or system. So that's possible. Any other questions?
Yeah,
Oh, yes, sir.
myself, Mohan Kumar is from Computer Science Department. By using statistical and then mathematical model or it may be computational model, by using this approach, we will come up with the one model actually. And then you are going to design the structure for that model. Will you tell that how exactly you are going to predict the life of that structure by using the mathematical and computational? Is there any way other than the probability functions to predict the life of the structure?
Yes, life prediction or reliability of that component is a major objective for most of the time. And you can predict, of course, you have to do the cyclic loading, right? Because service conditions change the so-called stimuli, external stimuli acting destruction. And the probability function has to be also there because there are variations in the load. I mean, you can think of like three-wheeler. It is designed for probably 3 people to sit in the back and then drive it. But you know, in reality, it is 12 people sitting there, right? So what I'm saying is it can be misused than what it is designed for. So the design has to account for those possibilities. So the life prediction is connected to these kinds of factors that influence the design. So life prediction, especially long-term durability, during the service condition, material also is degrading because it's exposed to environment, hot, heat, cold, others. So the material degradation has to also be accounted in predicting the life of the structure. So there are ways to bring all these elements, and probability is one way to say variability of the stimuli, variability of material properties. Because we cannot deterministically determine exactly it will last for 2 years, 6 months, 3 days. Okay, so it will only give the bandwidth, maybe 2 to 3 years, like that, 5 to 10 years, whatever that is.
What's the parameter you are going to use for deciding that?
Oh, it's not one parameter. Like I said, degradation of material properties, cyclic loading, and also the geometric configuration, which use what you call the hot spots, because the structure, every structure has places where most likely fail because of the stress concentrations. I'm just giving structural mechanics for. So it's not one thing.
Good afternoon, sir. Manish from Mechanical Department. Just you are talking about the application of computational mechanics in the area of structure property correlation. Do you have any information on, let's say, any particular frontiers of such research going on? Any particular examples of how computational mechanics is being applied to?
So again, I can go back to what I'm doing is this architecture, materials and structures, right? The properties of that, when we say word properties is, and ultimately it is the structural stiffness, strength and fracture, toughness, and fatigue life, all of these are kind of global properties of that structure. How are they connected to the architecture of the ligaments? What particular architecture is producing particular functionality? See, it may not be good for all of the terms I mentioned, fatigue life, durability, all that, right? So you find the most optimal situation. Or if there is a case, I only want this fatigue life, nothing else, then it's much easier because only one functionality. But you have multiple functionality, you have to find the optimization way. That means ultimately cast this into a what we call cost function, where various constraints are included in that cost function, which you minimize. So that is how we get there. There is no single answer for that type of thing. So really, these questions are very good because we tend to, in academic context, that there is one answer. There is no such thing, and there is no one answer that fits everything. So it's always a band in which we want to operate. And the design is based on that. It's not based on one number or one set of numbers. All right, thank you for coming to this lecture.
I express my gratitude to Professor Dr. Jane Reddy for a wonderful talk on computational mechanics. In a nutshell, you have taken us through how important it is in terms of computational mechanics and how constantly it is making an impact on science and industry in the various areas of engineering. Thank you so much for your work, sir. My heartfelt thank you to Dr. M. Pallam Raju, sir, for gracing our occasion. Thank you, sir. My sincere thanks to Professor Khanawil from Ramya University of Advanced Studies for gracing this distinguished lecture program. A big thank you to all the dignitaries, head of the departments, faculty, and students for being present today. Thank you, one and all.
So many